Good morning, children. Welcome to today's lesson on significant figures. Let us imagine a strong iron chain whose one of the links is weak. Obviously, the chain cannot be strong because of its weakest link. Similarly, if all the observations of an experiment have been made with great accuracy except one observation, then the inaccuracy in the single observation is going to mark the result unfavorable. When a mass, a length or a time or any quantity is measured in a scientific experiment, the result is known only within a certain accuracy. The inaccuracy or uncertainty can be caused by a number of factors ranging from the limitations of the measuring device itself to limitations associated with the senses and the skill of the experimenter and the number of measurements performed. In any case, the fact is that the observed values of experimental quantities have some uncertainties, and this should always be kept in mind when performing calculations with those values. One way to eliminate such errors is to measure the data with correct significant figures. Before we discuss about the significant figures, let me share the learning objectives of today's topic with you.
On completion of this topic, learners will be able to discuss the importance of significant figures, state the rules to determine the number of significant figures, discuss the various ambiguities involved while determining the number of significant figures, and suggest ways to remove the ambiguities. State other rules used to determine the number of significant figures. State the rules for arithmetic operations with significant figures. State the conventional rule followed to round off the uncertain digits. Discuss the importance of rounding off digits.
ਤੁਸੀਂ ਜਾਣਦੇ ਹੋ ਕਿ ਐਰਰ ਦਾ ਕੰਸਰਨ ਸਕੇਲ ਦੀ ਸਭ ਤੋਂ ਸਮਾਲ ਡਿਵੀਜ਼ਨ ਨਾਲ ਹੈ, ਲੀਸਟ ਕਾਊਂਟ ਭਾਵ ਸਭ ਤੋਂ ਘੱਟ. Error is about reading the smallest division, not about estimating value between two consecutive markings of the smallest divisions. ਉਦਾਹਰਣ ਵਜੋਂ ਕਨਵੈਨਸ਼ਨਲ ਤੌਰ ਤੇ 13.2 ਗ੍ਰਾਮ ਮਾਸ ਮੈਜ਼ਰ ਕਰਨ ਲਈ 0.1 ਗ੍ਰਾਮ ਦੀ ਅਨਸਰਟਨਿਟੀ ਹੁੰਦੀ ਹੈ ਅਤੇ ਕਿਹਾ ਜਾਂਦਾ ਹੈ ਕਿ ਨੀਅਰੈਸਟ 0.1 ਗ੍ਰਾਮ ਤੱਕ ਮੈਜ਼ਰ ਕੀਤਾ ਹੈ. ਦੂਜੇ ਸ਼ਬਦਾਂ ਵਿੱਚ ਅਸੀਂ ਲਾਸਟ ਡਿਜਿਟ ਬਾਰੇ ਅਨਿਸ਼ਚਿਤ ਜਾਂ ਅਨਸਰਟਨ ਹਾਂ. ਇਹ 2 ਹੋ ਸਕਦਾ ਹੈ ਜਾਂ 1 ਜਾਂ 3. ਇਸੇ ਤਰ੍ਹਾਂ 13.20 ਗ੍ਰਾਮ ਮਾਸ ਦੱਸਦਾ ਹੈ 0.01 ਗ੍ਰਾਮ ਤੱਕ ਦੀ ਐਬਸੋਲਿਊਟ ਅਨਸਰਟਨਿਟੀ. ਕਿਸੇ ਡੇਟਾ ਦੀ ਐਕਿਊਰੇਸੀ ਸਿਗਨੀਫੀਕੈਂਟ ਫਿਗਰ ਦੇ ਨੰਬਰ ਤੇ ਡਿਪੈਂਡ ਕਰਦੀ ਹੈ. We know that error is associated with the smallest division of the scale, that is its least count. Furthermore, error is about reading the smallest division, not about estimating value between two consecutive markings of smallest divisions. By convention, a mass measured to 13.2 gram is said to have an absolute uncertainty of 0.1 gram and is said to have been measured to the nearest 0.1 gram. In other words, we are somewhat uncertain about that last digit. It could be a 2, it could be a 1 or a 3. Similarly, a mass of 13.20 gram indicates an absolute uncertainty of 0.01 gram. Accuracy of a data depends upon the number of significant figures. The numbers of figures in a result that are known with some degree of reliability are simply the number of significant figures. For example, the number 13.2 is said to have 3 significant figures, whereas the number 13.20 is said to have 4 significant figures. Let us try to understand what is a significant figure. The significant figures express the accuracy with which a physical quantity may be expressed. In general, the number of digits whose values are accurately known in a particular measurement are called its significant figures. Significant figures comprises of digits which are known reliably and one last digit in the sequence which is not known reliably. We take an example of the measurement of length by a vernier scale. The measurement of the diameter of a sphere is reported as 1.32 centimeter. This value comprises of 3 digits, 1, 3 and 2. All 3 digits are significant as the same are measured by the instrument. The value indicates, however, that last digit is uncertain. We know that least count of vernier scale is 10 to power minus 4 meter, that is 10 to power minus 2 centimeter or 0.01 centimeter. There is a possibility of error which is equal to half of the least count, that is 0.005 centimeters. The reported value may therefore lie between 1.325 centimeter and 1.335 centimeter.
Let me show you the elements of measurement of a vernier scale. The reading on the main scale, that is upper scale, is taken for the 0 of vernier scale. The same is shown with red mark on the left. This reading is 1.3. We can see that 0 is between 1.3 and 1.4. In order to read the value between these intervals, we look for the division of vernier scale, which exactly coincides with the division mark on the main scale. Since 10 divisions of vernier scale are equal to 9 divisions on main scale, it ensures that one pair of marks will coincide. In this case, the second reading on the vernier scale is the best match. Hence, the final reading is 1.32.
Thus, significant figures in a measured quantity indicate the number of digits in which we have confidence. For example, a recorded figure of 2.32 means the quantity can be relied on as accurate to 3 significant figures, and a figure of 2.3212 is said to be accurate to 5 significant figures. In these examples, you can easily find the number of significant figures. It is because each digit used to express the magnitude of the measurement is significant. However, when we use the different systems of notation, this is not always the case. Let us write the average distance from the Earth to the Moon as S, which is equal to 377,000 kilometers or 3.77 into 10 to the power 5 kilometers. Does this number has 6 significant figures? No, this measurement is given to an accuracy of only 3 significant figures. The 3, the 7 and the 7 are significant. The last 3 zeros merely indicate the correct location of the decimal point. Similarly, 0.00232 centimeter contains only 3 significant figures. The zeros which merely locate a decimal point are not significant figures. To identify significant figures in the reported value, we have to follow certain rules. The first rule is all non-zero digits are significant figures. In order to formulate this rule, we consider the value of measured length as 51.32 centimeters. Can we drop any of the non-zero digits? No. This will change the magnitude of the length. Here, 51.32 centimeters contain 4 significant figures. It is sure that all non-zero digits are significant. However, zeros may or may not be significant. The second rule is all zeros occurring between 2 non-zero digits are significant. In order to formulate this rule, we consider the value of measured length as 5.03 centimeters. Now, can we drop 0 lying in between non-zeros 5 and 3 in this value? Dropping 0 will change the measured value. Hence, we cannot drop this 0. Does the decimal matter? No. Here, 0 and decimal both fall between non-zeros. It does not change the fact that 0 is part of the reported magnitude of the quantity. Therefore, according to rule number 2, all zeros between any 2 non-zeros are significant irrespective of the placement of decimal point. Can you tell me the number of significant figures in 110.007? Yes, 110.007 contains 6 significant figures. The third rule is all zeros to the right of a decimal point and to the left of a non-zero digit are never significant. Let us now express the given value of 5.03 decimeter in kilometer. The value would be 0.000503 kilometer. What do you think? By expressing a value in different unit would change significant figures. Changing significant figures will amount to changing precision and changing the least count of the measuring instrument. We cannot change least count of an instrument by mathematical manipulation. Here, 0.000503 kilometer contains 3 significant figures. Therefore, we can say that as per rule number 3, if the value is less than 1, then zeros between decimal point and the first non-zero digit are not significant. The fourth rule is the trailing zeros in a decimal number are significant. In other words, we can say that all zeros to the right of a decimal point are significant if they are not followed by a non-zero digit. For example, 20.00 contains 4 significant figures, and all zeros to the right of the last non-zero digit after the decimal point are significant. For example, 0.03200 contains 4 significant figures. The fifth rule is the trailing zeros in a non-decimal number are not treated as significant numbers. In other words, all zeros to the right of the last or rightmost non-zero digit are not significant. For example, measurement of the length of an object is 17.4 meter. It contains three significant figures. 17.4 meter is equal to 174 decimeter or 1740 centimeter or 17,400 millimeter. If you look closely, you will find that we have introduced one zero while expressing the value in centimeter and two zeros while expressing the value in millimeter. If we consider the trailing zero as significant, then it will again change the precision of the amount, which is not possible. The value of 1740 centimeter therefore has only three significant figures as originally measured. Therefore, according to rule number 5, the trailing zeros in a non-decimal number are not treated as significant numbers. However, the rule number 5 is further modified according to which all zeros to the right of the last non-zero digit are significant if they come from a measurement. For example, the distance between two objects is measured to exactly 30 centimeter. We want to distinguish this trailing zero. Trailing zeros appearing due to the measurement are reported with decimal point and treated as significant numbers. Now, the question arises, how to write a measurement of 30 centimeter in accordance with rule 4 so that it has decimal point to indicate that zeros are significant. We make use of scientific notation, which expresses a value in the powers of 10. Hence, we write different experimental values as 30 centimeter is equal to 3.0 into 10 to the power 1 centimeter. This representation shows that the value has two significant figures. We may write it as 3.0 into 10 to the power minus 1 meter or 3.0 into 10 to the power minus 4 kilometer. In this manner, we maintain the number of significant numbers if the measured value involves trailing zeros. To remove such ambiguities in determining the number of significant figures, the best way is to report every measurement in scientific notation, that is, in the power of 10. In the scientific notation, no confusion arises about the trailing zeros. They are always significant. The scientific notation is ideal for reporting measurement. Would you like to see an interesting example?
Let us take a cup of milk. Can you measure the quantity of milk in it? It may be 300 milliliters or 150 milliliters. I think it is about 200 milliliters. However, it may be 190 milliliters. I am not sure about it, as it is a rough estimation. Let us add a drop of water in it. We know that the volume of water drop is 0.05 milliliters.
Now, tell me what would be the new volume. Is it 200 milliliters or 200.05 milliliters or something else? I hope most of you will say it is 200.05 milliliters because you are adding 0.05 milliliters with 200 milliliters. But it is not correct. when you are adding 0.05 with 200, then it is supposed to be an accurate value. But I have told you it was a rough estimation. Here you are adding an accurate value, that is 0.05, to an inaccurate value, that is about 200. You cannot write 200 as 200.00 since you are not sure about the last two digits. I have said it is about 200, but you are assuming it to be 200.00. When you are writing 200.00, it means you know it accurately. In addition, when you are reporting a calculation, you can only report to the level of accuracy which is equal to the least significant value. ਅਸੀਂ ਜਾਣਦੇ ਹਾਂ ਕਿ ਫਿਜ਼ੀਕਲ ਕੁਆਂਟੀਟੀ ਦੂਜੀਆਂ ਮਾਤਰਾਵਾਂ ਤੇ ਨਿਰਭਰ ਕਰਦੀ ਹੈ। ਇਹਨਾਂ ਪ੍ਰਾਪਤ ਫਿਜ਼ੀਕਲ ਕੁਆਂਟੀਟੀਜ਼ ਦੀ ਪਰਖ ਗਣਿਤਿਕ ਆਪਰੇਸ਼ਨ ਜਿਵੇਂ ਐਡੀਸ਼ਨ, ਸਬਟ੍ਰੈਕਸ਼ਨ, ਮਲਟੀਪਲੀਕੇਸ਼ਨ ਅਤੇ ਡਿਵੀਜ਼ਨ ਆਦਿ ਮਿਣੀਆਂ ਹੋਈਆਂ ਮਾਤਰਾਵਾਂ ਨਾਲ ਕੀਤੀ ਜਾਂਦੀ ਹੈ। ਅਪਰੋਕਸੀਮੇਟ ਨੰਬਰਸ ਨੂੰ ਜੋੜ ਕੇ ਜਿਸ ਵਿੱਚ ਇੱਕ ਤੋਂ ਜ਼ਿਆਦਾ ਅਨਸਰਟਨ ਨੰਬਰ ਹੁੰਦਾ ਹੈ, ਉਸ ਰਿਜ਼ਲਟ ਨੂੰ ਰਾਉਂਡ ਆਫ ਕਰ ਦਿੱਤਾ ਜਾਂਦਾ ਹੈ। ਇਸ ਰਾਉਂਡ ਆਫ ਦੇ ਕੁਝ ਨਿਸ਼ਚਿਤ ਲਾਜ਼ ਹਨ ਜਿਸ ਨਾਲ ਬਹੁਤ ਵਾਰੀ ਐਪਰੋਪ੍ਰੀਏਟ ਸਿਗਨੀਫੀਕੈਂਟ ਫਿਗਰਸ ਪ੍ਰਾਪਤ ਹੁੰਦੀ ਹੈ। ਮੈਥਮੈਟੀਕਲ ਆਪਰੇਸ਼ਨ ਵਿੱਚ ਰਾਉਂਡਿੰਗ ਆਫ ਲਈ ਇੱਕ ਸਮਾਨ ਲਾਜ਼ ਵਰਤੇ ਜਾਂਦੇ ਹਨ। First rule for rounding off an uncertain digit is the preceding digit, that is uncertain digit of the significant figures, is raised by 1 if the digit following it is more than 5. For example, a value of 2.478 is rounded off to 2.48 to have 3 significant figures or to have 2 decimal places. Similarly, a number 1.346 is rounded off to 3 significant figures is 1.35. The second rule for rounding off is the preceding digit, that is uncertain digit of the significant figures, is left unchanged if the digit following it is less than 5. For example, a value of 2.534 is rounded off as 2.53 to have 3 significant figures or to have 2 decimal places. Similarly, a number 1.243 would be 1.24. But what if the number is 2.545 in which the insignificant digit is 5? Here the convention is that if the preceding digit is even, the insignificant digit is simply dropped, and if it is odd, the preceding digit is raised by 1. The odd preceding digit, that is uncertain digit of the significant figures, is raised by 1 if the digit following it is 5. According to rule 4, the even preceding digit, that is uncertain digit of the significant figures, is left unchanged if the digit following it is 5. Therefore, the number 2.545 rounded off to 3 significant figures becomes 2.54. On the other hand, the number 2.535 rounded off to 3 significant figures also becomes 2.54 since the preceding digit is odd. The rule 5 says, in any involved or complex multi-step calculation, in intermediate steps, we retain one digit more than the significant digits and round off to proper significant figures at the end of the calculation. We do not carry out rounding off in the intermediate steps. Finally, rule 6 is, in the case of physical constants like value of speed of light, gravitational constant, etc., or in case of mathematical constants like pi, we take values with the precision of the operand, having maximum precision, that is, maximum significant numbers or maximum decimal places. For example, a number known to be within many significant figures, such as in 2.99792,458 into 10 to the power 8 meter per second for the speed of light in vacuum, is rounded off to an approximate value 3 into 10 to the power 8 meter per second, which is often employed in computations. Finally, remember that exact numbers that appear in formulae like t equal to 2 pi under root L upon g have infinitely large number of significant figures. The value of pi is equal to 3.1415926, and it goes on, is known to a large number of significant figures. We may take the value as 3.142 or 3.14 for pi with limited number of significant figures as required in specific cases. Let us continue with the significant figures in addition and subtraction. The accuracy of a sum or a difference is limited to the accuracy of the least accurate observation in the addition and subtraction. However, from the example of a cup of milk, we can set up a rule for significant figures in addition and subtraction, according to which do not retain a greater number of decimal places in a result computed from addition and or subtraction than in the observation which has the least decimal places. To understand this, let us try an example. We have to work out the sum of three lengths: 23.123 centimeters, 120.1 centimeters and 80.2 centimeters. The arithmetic sum of lengths is 223.423 centimeters. In this example, third measured value of 80.2 centimeters has the least number of significant figures, that is 3. If we measure our result to the least significant figures, the result of sum should be 223 centimeters. But in physics, the sum and difference taken in this manner are discouraged, as it can be observed that the result is losing the least precision of 1 decimal point in the measured quantities. It is clear that we need to modify this result. The correct rule for addition and subtraction, therefore, is that result of addition or subtraction should retain as many decimal places as there are in the measured value, having least decimal places. Therefore, the result of addition in the example given above is 223.4 centimeters. When the values of different observations are multiplied or divided, the number of digits to be retained in the answer depends upon the number of significant figures in the weakest link. Significant numbers in multiplication and division. In multiplication or division, do not retain a greater number of significant figures in a result computed from multiplication and or division. Final result should retain as many significant figures as there are in the original number with the least significant figures. In multiplication or division, final result should retain as many significant figures as there are in the original number with the least significant figure. For example, if the speed of light is given as 3.00 into 10 to the power 8 meter per second, which has 3 significant figures, and 1 year, that is 365.25 days, which is equal to 3.1557 into 10 to the power 7 seconds, has 5 significant figures. Therefore, the light year is equal to 9.47 into 10 to the power 15 meters, that is, the final result should be of 3 significant figures. Let us have a look on one more example. If the mass of an object is measured to be, say, 4.237 gram, it has 4 significant figures, and its volume is measured to be 2.51 cubic centimeters. Then its density by mere arithmetic division is 1.688047,808.76 gram per cubic centimeter, up to 11 decimal places. It would be clearly absurd and irrelevant to record the calculated value of density to such a precision when the measurements on which the value is based have much less precision. The density should be reported to 3 significant figures only. Therefore, the correct density would be 1.69 gram per cubic centimeter. While recording the numbers in significant figures, it can be observed that greater the number of significant figures obtained when making a measurement, more accurate is the measurement. From this discussion, important aspects of significant figures are: changing units does not change significant figures. Representation of a value in scientific form having a power of 10 does not change significant figures of the value. We should not add on zeros unnecessarily, as the same would destroy the meaning of the value with respect to the error involved in the measurement. I hope you are well versed with the significant figures and their importance. Let us summarize today's topic. In general, the numbers of digits whose values are accurately known in a particular measurement are called as significant figures. The number of digits whose values are accurately known in a particular measurement are called its significant figures. The rule 1 is all non-zero digits are significant figures. The rule 2 says all zeros occurring between two non-zero digits are significant. The rule 3 is all zeros to the right of a decimal point and to the left of a non-zero digit are never significant. According to rule 4, the trailing zeros in a decimal number are significant. The rule 5 says the trailing zeros in a non-decimal number are not treated as significant numbers. All zeros to the right of the last non-zero digit are significant if they come from a measurement. Significant numbers in addition and subtraction do not retain a greater number of decimal places in a result computed from addition and or subtraction than in the observation which has the least decimal places. Significant numbers in multiplication and division. In multiplication or division, final result should retain as many significant figures as there are in the original number with the least significant figures. The result of computation with approximate numbers which contain more than one uncertain digit should be rounded off. The rules for rounding off the numbers to the appropriate significant figures are: Rule 1 is the preceding digit, that is, uncertain digit of the significant figures, is raised by 1 if the digit following it is more than 5. The rule 2 is the preceding digit, that is, uncertain digit of the significant figures, is left unchanged if the digit following it is less than 5. The rule 3 is the odd preceding digit, that is, uncertain digit of the significant figures, is raised by 1 if the digit following it is 5. According to rule 4, the even preceding digit, that is, uncertain digit of the significant figures, is left unchanged if the digit following it is 5. The rule 5 is, in any involved or complex multi-step calculation, in intermediate steps, we retain one digit more than the significant digits and round off to proper significant figures at the end of the calculation. We do not carry out rounding off in the intermediate steps. And the rule 6 is, in the case of physical constants like value of speed of light, gravitational constant, etc., or in the case of mathematical constants like pi, we take values with the precision of the operand having maximum precision, that is, maximum significant numbers or maximum decimal places. So now we come to the end of today's topic. I am confident that you have enjoyed the lesson and are looking forward to the next class. Thank you for your attention and see you next time.